All right, let's actually crunch some numbers. So a good chunk of your homework is going to ask you to either start with an eigenvector and find the eigenvalue, or the other way around, start with the eigenvalue and find the eigenvector. So let's do one of each of those. We are graduating to 3 by 3 matrices here. So the first one, we've got a 3 by 3, and I'm claiming that 1, 1, 1 is an eigenvector for this matrix, and we want to find the eigenvalue. So what's the eigenvalue? And that's easy enough. Keep in mind the equation here, the basic equation, is to say that multiplying the matrix by the eigenvector should be the same as multiplying the eigenvalue by the eigenvector. At the moment, we've got A and we've got V, and we just need to figure out lambda. So all we really need to do is sort of fill those pieces in. So there's A, there's V, and we'll see what we get coming out. So 1, 1, 1 just means 1 of the first column plus 1 of the second column plus 1 of the third column, so that's easy enough to add up. So that would be 10, 10, 10. And to be a little more explicit, that would be 10 times 1, 1, 1. Okay, so easy enough. Nice that the numbers were simple here. But that's the process you would do anytime you have an eigenvector, is you just say, okay, let's watch it work. Multiply it by the matrix and see what comes out, and it should be a multiple of what you put in. And in this case, the eigenvalue that goes with that particular eigenvector is 10. Fair enough. So that's one way around. The other way around is supposing you just have the lambda, you just have the eigenvalue. You say, I know I'm going to multiply this by something, some v, and what's going to come out is, oops, not lambda, we know lambda. What's going to come out is -2 times v. And that probably looks like a harder problem. And it is a harder problem, but it's not undoable by any means. Let's do a little bit of algebra. We are in linear algebra after all, so let's make use of the power of algebra here. And just start with our basic eigenvector, eigenvalue equation. And I'm going to move both terms to one side. Do keep in mind when I write 0 here, I mean a 0 vector. So if it's a 3 by 3, this would be 0, 0, 0 as a vector. So this 0 is here to stand for a vector. If it's helpful, you can put the little vector brackets around it. But anyway, on the left-hand side here, I want to factor the v. Now before I do that, I can't exactly do a minus just a constant, but notice that I can always put an identity matrix in here. And now I can factor. I can do a minus lambda I times v equals 0. So really, and I'm trying to solve for v, right? That was the whole point. That's why we're moving things to one side and factoring, so we can just get 1v instead of 2. Notice that a, whatever that's going to be, minus lambda I. What does lambda I look like? It looks like, in our case, it looks like -2 times I. But in general, it's going to look like lambda times times an I. And lambda times a matrix multiplies all the entries in the matrix, so that's going to look like A minus lambda 0, 0, 0, lambda 0, 0, 0, lambda, oops, square bracket. I'm just taking the very long way here of saying what does it look like when you do A minus a lambda. And it essentially means you subtract the lambda from the main diagonal of A. And once you get done doing that, that will be a single matrix, oops, times V, I left my V off, times V equals 0. It's just a homogeneous system of equations. Homogeneous equal to 0, right? So let's take this general idea and apply it specifically over here and say we want to do B minus lambda I times V equals 0. So for us, that's going to look like a 3 by 3 matrix times V equals the 0 vector. And B minus negative 2 along the main diagonal. Keep in mind I only gives you lambda on the main diagonal. So that will be 2 minus negative 2, or 2 plus 2, so 4. 5, 4. The other entries aren't changed. 3, 1 minus negative 2 is 3. Minus 1, and 1, 2, 3 minus negative 2 is 5. So this is still a little bit of work, but this is very solvable, right? We know how to do this sort of thing. We can just row reduce a 3 by 4 matrix. So we've got 4, 5, 4, 0, 3, 3, negative 1, 0, and 1, 2, 5, 0. And as soon as we solve that, we will have the eigenvector that goes with this particular eigenvalue of negative 2. So let's figure that out. Okay, so grab your calculator and reduce that. And we get some fractions this time, which is okay. And notice we do have a free variable here, which is good. If the only solution to the homogeneous system was 0, 0, 0, keep in mind we're not allowing 0, 0, 0 as an eigenvector, so that's not what we want. We need something else besides that. Okay, so let's take a look at what our equations would translate into down here. The first one would say x1 is 17 thirds times x3, and the next one would say x2 is 16 thirds times x3, and the last one would say x3 is x3. So the eigenvector that corresponds to negative 2 is any multiple of 17 thirds, 16 thirds, 1. You can certainly use, and this by the way is always true, any multiple of an eigenvector is also an eigenvector. So up here in the previous example, if I started with 2, 2, 2, I would have gotten 20, 20, 20 here. It still would have been the same 10 times what we started with. But anyway, any multiple of this is going to be an eigenvector. So just for convenience sake, I might pick x3 to be 3 and say that the eigenvector that goes with negative 2 would be 17, 16, 3. So a little bit more work, but as you get used to the process, I think you'll get pretty comfortable with probably not having to write out this part right here. You'll probably be able to jump probably straight to writing this down, right? We know every time it's going to be augmented with 0, and it's going to have the eigenvalue subtracted straight from the main diagonal. And then just row reduce that, finds the corresponding eigenvector that comes out. I should point out that since the eigenvectors and eigenvalues are the solution to a homogeneous system of equations, they are the null space for a particular vector, which means they are a vector space, which means you get one more cool word. That particular vector space, that is the null space for this particular funky matrix, gets to be called the eigenspace. Now we're getting some good techno speak. Okay, we'll look at a couple more ideas in the next video, but this is giving us some basic number crunching of saying if you have one piece, how do you find the other from an eigenvector to an eigenvalue or vice versa.